Welcome to this Leaving Cert Higher Level Trigonometry video where we're going to be focusing on trigonometric identities. So we're going to be focusing on little informal proofs and working with the identities, and we're going to focus on using page 13, 14, 15 and 16 in your Formula and Tables book. So it'd be a good idea to have those open in front of you, and I will show you exactly where we're looking for each one, but just for you to get familiar with your log tables. So first thing we're going to talk about is an equation versus an identity. So an identity is an equation that's true for all values of the variable for which the expressions are defined. So you would have seen identities in algebra when we would have had unknown coefficients. And how we would have identified identities in that case would have been the statement is true for all values of x element of or. So basically saying we know it's true for all x, so we want to find maybe a, b, c. So the main difference between an identity and an equation is an identity, we are not looking to solve it. We're not looking to find a specific value for our variable. And it's going to be really important that we understand the difference between our coefficient, our constants, and our variables when we're in algebra. For us, the identities we're going to work with in this video are trigonometric identities. So work through this, and basically what we're trying to do in each of these questions is to show that one side of the identity equals the other and work through them without solving for the angle. So that angle might be A, it might be theta, but we don't want to solve for it. So we're going to focus on page 13, 14, 15 and 16. On page 13, we have some identities up here at the top. There are little formulas that hold true. We have tan is sine over cos. We have cot, which is cos over sine A. Sec A is 1 over cos A. Cosec A is 1 over sine A. We have then over on the right hand side, cos squared A plus sine squared A equals 1. They're all linked to that unit circle that's in the middle, and so on. So we're going to use these first set of identities to help prove this identity here. So example 1, prove that the identity sec A minus tan A times sine A is equal to cos A. So basically, you are better to work with where you have more information. So first thing I'm going to do, just because it's trigonometry and there's a lot of letters and it looks kind of different to what we would usually see in algebra. So I like to really clearly show either through highlighting or boxing what exactly we're working with. We're going to start subbing in what we can. So sec A, we know that that is actually given as 1 over cos of A. Minus tan of A. So tan of A is actually given as sine A over cos A. And that's multiplied by sine A. And we're trying to show that that equals cos of A. So we're going to keep working down this left hand side. We have two fractions here, and there is a common denominator. So my common denominator here is cos of A. When we multiply sine A by sine A, we're going to get sine squared A. So the notation is to have your squared against the sine. So we have that little power 2 comes into the just after the sine, and that means sine A by sine A. And we want to show that that equals cos A. Now, the next thing I'm going to use is a version of this formula here. So this can be rearranged. I'll rearrange it down here. In any way we want, but the way we're going to work it is cos squared A is equal to 1 minus sine squared A. So that's the rearranging. So we have cos squared A divided by cos of A, and that equals cos A. And this simplifies down to cos A equals cos A. So we have exactly what we want, QED. So example 2, first thing I'm going to do, put a box around this so I know exactly what I'm working with. And it wants us to prove this identity here. So tan of theta, I'm going to just sub in what I can. Sine of A, cos over cos of A. Square root of 1 minus sine squared. Oh, so I was doing A's. Question is actually thetas. Let's keep an eye on that. If you kind of work through it, really depends on the question, but you could lose some marks, so just be careful. So 1 minus sine squared theta, we just went through that. That is cos squared theta. Cleaning that up, the square root of a square, effectively they cancel. So cos of theta, so this will give me cos of theta. We're trying to show that these all equal sine of theta, and here we have cos on the bottom, cos on the top. They divide into each other or cancel, and we get sine of theta is equal to sine of theta, QED. So example 3, prove that tan of theta plus sine of theta all over sec of theta plus 1 is equal to sine of theta. So again, we're going to go straight into what we can substitute. So sine of theta over cos of theta plus sine of theta all over 1 over cos of theta plus 1. Not a huge fan of working with fractions like this, so I would always suggest that you break it into top line, bottom line. So what we have here is actually a complex fraction. So where there's fractions within fractions, and that can lead to a lot of problems if you don't deal with it correctly. So the easiest way I would say to deal with it is separately. So TL stands for top line, BL for bottom line. So I've just brought the top line over here. I want a common denominator. Sine of theta all over cos of theta plus sine theta cos theta. If you wanted at this point, we can pull out, so highest common factor sine of theta, 1 plus cos of theta all over cos of theta. Then we go to the bottom line, and again common denominator 1 plus cos theta all over cos theta. Going back to working with your fractions, think to your algebra. Top line divided by bottom line. Instead of division, we multiply by the reciprocal. So what we actually get is our top line, which is sine of theta, 1 plus cos theta, all over cos of theta. We should divide it by the bottom line, but instead we multiply by the reciprocal of the bottom line, which means we flip the fraction. Reciprocal, we flip the fraction. 1 plus cos of theta, and our cos thetas cancel here and here. 1 plus cos theta cancels here and here, and that equals sine of theta, QED. So now we're going to move to page 16 of our log tables, and we're going to focus on the sine rule and the cos, which are given here. So example 4, prove that in any triangle C cos B minus B cos C is C squared minus B squared over A. So we're going to work with the cosine rule here, and we can rearrange our cosine rule. So I'm going to take the cosine rule as is, so this one here, and I'm going to rearrange that so that I get cos A is equal to A squared minus B squared minus C squared all over minus 2BC. Changing the signs on that is cos of A is equal to B squared plus C squared minus A squared all over 2BC. And notice that this letter here will match this one here. So that is cosine rule rearranged, and we're going to use that for this example. So we want C cos of B minus B cos of C. So I'm going to just put a little box around this. That was kind of our workings to the side. So we get C. Now cos of B, following this formula, it's going to be A squared plus C squared minus B squared all over 2AC. So remember, B is here, so we're talking about our B being here. Minus B. Now cos C is going to be A squared plus B squared minus C squared all over 2AB. And again, there's my C and my C, and I want to tidy this up. First thing I'm going to do, my C's cancel here and my B's cancel here, so I'm left over 2A for both of them, and that means I effectively have a common denominator. So I'm going to combine, and I get A squared plus C squared minus B squared minus A squared plus B squared minus C squared all over 2A. Cleaning that up, I get A squared plus C squared minus B squared minus A squared minus B squared plus C squared. And my A's will cancel, and I'm left with 2C squared minus 2. Sorry, no, I actually forgot my bottom line in my rush, so that's all over 2A. And that gives me 2C squared minus 2B squared all over 2A. We can pull out a 2, so C squared minus B squared all over 2A. 2's cancel, and I'm left with C squared minus B squared over A, which is exactly what we wanted. QED. So the next thing we're going to look at are these formulae here. So these are our compound angle formula. So compound is where we add together. So notice that these are compounds with pluses and with minuses. So we have the cos of A plus B, sine of A plus B, tan of A plus B, cos of A minus B, sine of A minus B, and tan of A minus B. So example 5 is express in third form sine of 15 degrees and tan of 105 degrees. So in third form means basically I want to use page 13 in my log tables. That little box on page 13 is going to help us greatly. When we want to use page 13 but the angle size is not there. So for example, 15 degrees is not on page 13 of the log tables. And we can use the compound formula to help us. So we can do some kind of compound or mixing of the angles here. Now, here are a few different ways we could do it. Now, 15 degrees is not going to be two things added together, but you could have the 15 degrees could be made up of 45 degrees minus 30 or 60 minus 45. Either will work. I'm going to write this as sine of 45 degrees minus 30 degrees. So I'm using that compound formula here. So that gives sine of A, sine of 45 degrees, cos of B, cos of 30 degrees, minus cos of A, cos of 45 degrees, sine of B, sine of 30 degrees. And now I can go into my log tables and get all these in third form, never touch my calculator. 1 over root 2 times cos of 30, root 3 over 2, minus cos of 45, 1 over root 2, and sine of 30 degrees is a half. So we can clean that up a little bit. Root 3 over 2 root 2. minus 1 over 2 root 2. And that is as simple as we can make it. So that's our answer. So let's talk about the tan of 105 degrees. So looking at our log tables, what could we add together? So in this case, 45 degrees and 60. So let's go with that. So the tan of, you can do 45 degrees plus 60 or 60 plus 45. Order won't matter, you'll get exactly the same answer. And we're using this formula here. So this is the tan of 45 degrees plus the tan of 60 all over 1 minus tan of 45 tan of 60. So tan of 45 1 plus tan of 60 root 3 all over 1 minus 1 times root 3. So we're left with 1 plus root 3 over 1 minus root 3. Now, technically, this is not a good way to leave this. It'd be okay if we had a third as one term underneath, but this mix of rational and irrational numbers is not great. So what we're going to do, we're going to rationalize the denominator. So to remind you, rationalize the denominator is where you multiply above and below by the conjugate of the bottom or the conjugate of the denominator. Conjugate is where we change the sign in the middle. So working that through, effectively you get 1 plus root 3 squared on top. So that's square the first plus twice the first by the second plus square the second. Bottom line is 1 minus square the second. So that's kind of like a difference of two squares. The first term squared minus second term squared. Cleaning that up, we get 4 plus 2 root 3 all over minus 2. We can clean that up a bit. So divide minus 2 into both sides. So we get minus 2 plus, well, minus 2 minus 1 root 2. Actually, I don't even need that one. We just need a root 2. So all we've done here is we divide minus 2 into 4 and get minus 2. Plus 2 divided by minus 2 and it gives us a minus root 3. So again, minus root 3. So final answer is minus 2 minus root 3. So now they've given us a tan A and tan B. Find the value of A plus B without using a calculator. Again, what we're going to use here is we're dealing with tans and we're dealing with compound angles, so A plus B. So we're going to work off this. So we have tan of A plus B is going to be the tan of A, which is a quarter, plus the tan of B, which is 3/5, all over 1 minus a quarter times 3 over 5. That gives us the tan of A plus B is equal to, now a few different ways that you can approach this. If you want to do at this point lowest common denominator and add them, that's absolutely fine. So that's 5 plus 12, so that gives us 17 over 20. You can stick that into your calculator either if you prefer. And here we get 1 minus 3 over 20. So for us, we'll clean up tan of the plus beta. That gives us 17 over 20 all over minus 17 over 20. Sorry, plus 17 over 20. 17 over 20 by 17 over 20. And that simplifies down to 1. So that gives me the tan of A plus B equals 1. So now I don't even need my calculator. I'm going back to page 13 and I can see that it's the tan of 45 degrees. So A plus B equals 45 degree. So without ever having worked out A and B individually, I've been able to work out the compound angle A plus B. So our last example of these compound formula, prove that the sine of A plus B divided by the cos of A cos of B is equal to tan A plus tan B. Okay, so sometimes we see things like this. It can be a bit like, oh, where do we start? So cos of A, cos of B, tan of B. There's not a lot we can do with that. The thing that we can really do something with is this sine A plus B. So we're dealing with this formula here. So let's work that out. So this is going to be the sine of A cos of B plus cos of A sine of B all over cos of A cos of B. And what I'm going to do now is I'm actually going to separate that into two fractions. So we're going to have sine of A cos of B all over cos of A cos of B. So this is like the backward step to combining my fractions. I'm going to separate it out. Sometimes separating it out gives us a little bit more control on what we're doing, and you'll see now what exactly we'll be able to do. So cos of A cos of B. Now, because I've separated it, now I'm going to be able to do some cancelling. Remember, I couldn't cancel on the line above because there was a big plus in the middle. Cancelling is effectively dividing, so dividing can only happen when we have multiplication. So now we're left with sine of A over the cos of A plus sine of B over the cos of B. So if you go back to page 13, and on the top left hand corner we will find a little formula there to tell us that the tan of A is sine of A over cos of A, which means what we've just worked out, this is the tan of A plus tan of B, and that's exactly what they asked, QED. So the next set of formula we're going to look at, again on page 14, are our double angle formulas. So that is basically where we have doubled the angle. So there's a 2 in front of our angle. So the sine of 2A, the cos of 2A. We also have here two squared terms, so cos squared A and sine squared A, because both of those formulas contain a double angle. So remember, they work both ways. We also have some tan squareds going on, and cos squared, sine squared in there as well. So we have a little bit to work with. Let's go straight into an example of express sine of 3A in terms of sine of A. Now, how are we using the double angle formula for this? Well, not only are we going to use the double angle formula, we're also going to use formula we've used before. So we're going to rewrite sine of 3A as sine of 2A plus A. And if we go back to the top of page 14, what happens if I have sine of A plus sine of B? We have the sine of the first angle, cos of the second angle, plus cos of the first angle, sine of the second angle. Okay, so that's our little piece now. We then want to split this 2A and the sine 2A and the cos 2A using our above formula. So sine 2A and cos 2A. Okay, now we could also for cos use this one or this one. So let's just do our first substitution for sine of 2a. That will definitely be fine, and then see where we're going from there. So sine of 2a is 2 sine of a cos of a times cos of a. And now I want to do plus. So do I want to start putting in cos squareds and sine squareds? Probably not. What we will actually work with is this one here. Let me rewrite the three pieces. So we're actually going to work with this one here. Now, in order to see that, you might want to clean up this little bit first. Because we'll have 2 sine a cos squared a. So I could put in the one above it, but that will give me causes. And remember, I want to write everything here in terms of sine. So we're going to focus on this little formula here. Now I can rearrange this to give 2 sine squared a is equal to 1 minus cos of 2a, and rearrange it again. Cos of 2a is 1 minus 2 sine squared a. So that's the substitution we're going to use. 1 minus 2 sine squared a, sine of a. Now, at the moment, I've multiplied out the first piece, but I'm not sure about cos squared a, because remember, I want everything in terms of sine. So multiplying this out, we get sine of a minus 2 sine cubed a. So I want to sub in for cos squared a, and I want to sub in for cos squared a, so I have something in terms of sine. The thing that I'm going to sub in is actually on page 13, and that is sine squared a plus cos squared a equals 1. So cos squared a is 1 minus sine squared a. So that changes that, so that's okay. And then I get a sine a minus 2 sine cubed a. Multiply that out. 2 sine a minus 2 sine cubed a plus sine of a minus 2 sine cubed a, and that can clean up to 3 sine a minus 4 sine cubed a. So now we've taken sine of 3a and we've replaced it and written it all in terms of sine. Let me just highlight this. Sine of a. So let's jump into a number example. So given that theta is acute and that the tan of theta is equal to 1 over 2, evaluate sine of 2 theta and cos of 2 theta. So we're going to work with our formulas here, which will be sine of 2 theta. We're going to work with this one here. So that is the sine, 2 sine of theta cos of theta. So if I can break that down into sine and cos, so if I can get tan and turn it into sine and cos, I'll be able to fill that formula in. For cos of 2 theta, best thing we can do for this is this formula here, which is cos squared theta minus sine squared theta. Now just remember that means cos of theta all to be squared minus sine of theta all to be squared. So we need to basically at this point change or work with our tan of theta to figure out sine and cos. So we covered this in the Junior Cert revision video, but basically if I know sine, cos or tan, I can put it onto a little triangle. So tan is opposite over adjacent. Working that through, so let's just say that's x for a second, we can get x squared squared equals 1 squared plus 2 squared. So 1 plus 4, so x squared equals 5, so x is equal to the square root of 5. And that gives us, there's my opposite, there's my adjacent, now there's my hypotenuse. So that allows me to figure out sine and cos. So here, 2 times sine of theta, opposite over hypotenuse, 1 over root 5. Cos of theta, adjacent over hypotenuse, 2 over root 5. So that gives us 4 over 5. Here we want the cos squared, so 2 over root 5 squared minus sine 1 over root 5 squared. So that gives us 4 over 5 minus 1 over 5, which is equal to 3 over 5. Okay, so show that sine of 2a all over 1 plus cos of 2a equals tan of 2a. So sine of 2a, we have 2 sine a cos a all over 1 plus. Now, cos is always a lot more difficult to work with because we have so many options. Well, we have 3 options really here that we can work with. So it's really trying to figure out which one is going to work best for us. We want to get tan. So think about that for a second. So tan, realistically, if we're working with this, is sine over cos. So I have a sine on the top line and I wanted to cancel with a cos. So let's work with getting cos underneath the line. So if I want to get cos underneath the line, I'm going to work with this one. Now this one is not in the format that I need, so we can rearrange this so that we get 2 cos squared a is equal to 1 plus cos of 2a. Rearranging that again, cos of 2a is 2 cos squared a minus 1. A little bit of cleanup. 2 sine a cos of a, 1 plus 2 cos squared a minus 1. The plus 1 minus 1 goes to 0. And we get 2 cos squared a. Now we have 2's will cancel. One of my causes will cancel with one of my causes above. Remember, everything is multiplying. This is fine to do. Sine of a over cos of a. And that breaks down to tan of a, exactly what we were asked. QED. Okay, so example 11, show that cos to the power of 4 theta minus sine to the power of 4 theta is cos of 2 theta. We should be able to work on either side, but I think it'd be just as easy to work here. So what you might notice is we actually have a difference of 2 squared. So in the first one we have a cos squared theta that's squared. In the second term we have a sine squared theta that is squared. Difference of 2 squared gives us cos squared theta minus sine squared theta. Here we have cos squared theta plus sine squared theta. Above here we're told that actually cos squared theta minus sine squared theta gives me cos of 2 theta. And from page 13, cos squared theta plus sine squared theta gives me 1. So that actually equals cos of 2 theta. And that is exactly what we want. Proven. So example 12, if cos of 2 theta is equal to 7 over 25, find the values of sine of theta for 0 degrees is less than or equal to theta is less than or equal to 360 degrees. So first thing we want to do is convert sine of 2 theta, cos of 2 theta into sine. We're going to use this formula here. When we rearrange this formula, we get cos of 2 theta is equal to 1 minus 2 sine squared a. So we know that 1 minus 2 sine squared, that should be theta, is equal to 7 over 25. So rearranging this, we get 2 sine squared theta is 1 minus 7 over 25. And that gives us 2 sine squared theta is equal to 18 over 25. So now we're going to divide it by 2 and we get sine squared theta is equal to 9 over 25. That gives us sine of theta is equal to the square root of 9 over the square root of 25, or just the square root of the whole thing. But when we do the square root, you have to remember to put in a plus and a minus. So sine of theta is equal to plus or minus 3 over 5. So remember, with our unit circle, we have C is positive, all are positive, sine is positive, and tan is positive. So sine can be both positive and negative between 0 and 360 degrees. So our final answer is plus or minus 3 over 5. So example 13, if sine of 2a is equal to 3 over 5, find two values for tan of a where a is between 0 and 90 degrees. So the first thing we want to do is to find a formula that converts sine into tan. So sine of 2a into tan, and we're going to use this formula here. And we get sine of 2a is equal to 2 tan of a all over 1 plus tan squared a. So we know 2 tan of a over 1 plus tan squared a is going to equal 3 over 5. So multiplying both sides by the denominators gives us 5 times 2 tan of a and 3 times 1 plus tan squared a. Multiplying that out, we get 10 tan a equals 3 plus 3 tan squared a. Rearranging that, we can get 3 tan squared a minus 10 tan of a plus 3 equals 0. Now what might be easier is to use a substitution. So let x equal tan of a. So that squared looks a little cubed. So let me just clean this up too. So what we end up with is 3x squared minus 10x plus 3 equals 0. This might make it easier to solve. If you prefer and you're happy to leave it as tans, that's absolutely perfect. When you use guide number, we'll bring it down and you'll end up with the brackets as 3x minus 1 and 3x minus 1 and x minus 3, and you get two answers. X is equal to a third and x is equal to 3. So two values of tan of a. Tan of a is equal to a third and tan of a is equal to 3. Remember, it did tell us that we were talking about 0 and 90 being the first quadrant, C, A, S, T. That means we're talking about where tan is positive, and both of our answers here are positive. So now we're going to look at our next set of formula, and they appear on page 15 of our log tables, and they're the product to sum and difference. So page 15 contains two sets of formula, and basically they work and they're the opposites of each other. So one is converting products, so multiplication, to sums and differences, so adding and subtracting. The bottom one will change or convert the sums, so adding, or the differences, subtraction, to products, so multiplication. So let's start working with the first set, products to sum and differences. So example 14, express 2 cos of 3x sine x as a sum or difference. So the first thing we want to do is identify which formula we want to work with. So we have 2 cos and then sine. So the first one is cos, the second one is sine and then cos, third one is sine, the fourth one is cos and then sine. So from our formula, do a little bit of highlighting. So there's A, so our A is 3x, and we'll go green for B. So our B is x. So what this is going to look like is sine of A plus B minus sine of A minus B. So that gives us the sine of 4x minus the sine of 2x. So example 15, express cos of theta, cos of 5 theta as a sum or difference. So the first thing I'm going to suggest that we do is just rearrange it. Remember, it doesn't matter what order we multiply in. Multiplication is commutative. So I'm going to change it so that the big one is always in front. This is to help us with the differences so we don't get negative angles and we don't have to overcomplicate the question. So we've got cos and cos, so we're going to work with this formula here. And notice that we don't have the 2 in front of it, so we're going to have to deal with that. So A is 5 theta, B is theta. So because we don't have that 2 in front of it, our answer is going to end up with a half in front of the whole question. So we're going to have the cos of A, which is 5 theta, plus B, which is theta, plus cos of A, which is 5 theta, minus B, which is theta. Now it would work out the other way, but you just have to mess around with negative angles, and we don't really want to have to do that. We want to do as little as possible. So cleaning this up, we get cos of 6 theta plus cos of 4 theta. And that's our final answer. So now we're going to look at the second set of formula on that page, and that's working the opposite way. So sums and differences to products. So example 16. Express cos of 5a plus cos of 3a as a product. So again, first thing I'm going to do is identify which formula I'm talking about. So I have 2 causes and I'm adding them, so it's this formula here. My A comes across the formula like this, and our B comes across our formula like this. B is 3a, and our A is 5a. So what we end up with is 2 cos of 5a plus 3a over 2 cos of 5a minus 3a over 2. 2 cos, I get 8a over 2, and cos of 2a over 2, and that gives us final answer 2 cos of 4a cos of a. So example 17, express 3a minus sine a as a product. So we're going to find a formula that works for us. So we have sine of 3a, sine of a. So we're going to use this bottom one here, which is sine minus sine. Our a in this question is 3a, and our b is a, just to be very confusing. And we end up with an answer of 2 cos of a, which is 3a, so the yellow one, plus the green one over 2. Now I've written it in as a b rather than a. It's going to end up confusing me no matter what. So a sine of a, it's the yellow one, 3a minus b, which is a, all over 2. Doing a bit of cleanup on that, 2 cos of 4a over 2, sine of 2a over 2, and that's 2 cos of 2a, sine of a. So example 18, show that sine of 3a minus sine of 2a plus sine of a all over cos of 3a plus cos of a minus cos of 2a equals tan of a. So we're going to have to start combining some of these terms. Now, what we might jump and do is, let's say, combine these two terms. But if I was to combine those two terms, remember that I'm going to be adding these angles and dividing by 2. If I add those, that will give me 5a, and it won't divide evenly by 2. My final answer has a 2a here, and that means that I want to focus on trying to get those at least to an even number. So 3 plus 2 divided by 2, that's not going to be very helpful. So what we're going to do, we're going to rearrange that top line into a way that works for us. So I'm going to take that top line, and I'm going to take the top line and write it as sine of 3a. Then I'm going to add my sine of a, and then I'm going to take away the sine of 2a. I'm then going to combine these first two terms. Remember, I'd have the same issue if I added sine of 2a plus sine of a. So I have a 3a here, and I have an a here. With regards formula, I have sine plus sine, so I'm dealing with this formula here, which means a, and b, b, b. So my yellow, my green, just to try keep it straight. So 2 sine of 3a plus a over 2. And then I have cos of 3a minus a over 2. Don't forget, we do have the sine of 2a here as well. So tidying this up, I get 2 sine 4a over 2. I'm going to go straight to 2a. And cos of 2a over 2, which is a, minus sine of 2a. Notice now we actually have a sine of 2a that's common. So I'm going to pull that out in front. And I'm left with 2 cos of a minus 1. So that's my top line at the moment. That's top line. With my bottom line, I'm not going to run into the same issue that I had with the top line, because when I add 3a and a, it'll be okay, and when I take that away, it'll be okay. So I'm going to change up my color slightly. So there's 3a and a. So the formula I'm going to use for cos plus cos is this one up here. And we have a's in the blue and b's in the purple. So working with the cos of 3a plus the cos of a, we get 2 cos of 3a plus a over 2 and cos of 3a minus a over 2, and then we still have a minus cos of 2a here. So cleaning that up, we get 2 cos of 4a over 2, which is 2a, cos of 2a over 2, which is a, minus cos of 2a. So we get 2 cos, we have a cos of 2a that is common. So we pull that out in front, and we're left with 2 cos a minus 1. Now we can bring our fraction back together. So there's my bottom line. So my top line, bottom line, there's my top line, bottom line. So there's no problem doing this in a question as long as you've clearly labelled where you're going. I don't like working with fractions when there's quite a lot to do with them, so I'll tend to take the top line, then the bottom line, and then bring it back together. So bringing my fraction back together, we get sine of 2a, 2 cos a minus 1. The bottom line is cos of 2a, 2 cos a minus 1. Because we have a 2 cos a minus 1 on the top and on the bottom, that cancels, and we have sine over cos, which from page 13 is tan of 2a. So we're going to do a little bit of work on the inverse trigonometric functions now, and I just want to remind you that on page 13 we have this really helpful little table. It gives us the main angles in both degrees and radians, and it gives us the answers for sine, cos, and tan. This is also the page that we get the unit circle, and we have our negative angle formulas, and we also have tan and some other important formula like cos squared a plus sine squared a equals 1. But our focus for the next few questions is going to be at the bottom of that page 13. So example 19, write down the value of each of the following angles in the range 0 to 90 degrees. So you know that, hopefully you know that the year is a unit circle and that we have both positive and negative values for sine, cos and tan depending on where they fall in that unit circle. If you need to go back over that, there is a separate trigonometric video that covers that as well as functions and equations. For this question, we're specifically looking at just from 0 to 90. So we're looking for the sine inverse of a half. So I'm going along the sine line till I find a half, and they've said 0 degrees to 90 degrees, so we're working in degrees, so that gives me 30 degrees. If it was radians, I'd have pi over 6. Cos inverse of 1 over root 2. So cos line go to 1 over root 2, and that gives me 45 degrees. Tan inverse of root 3, go to the tan line, find root 3, that's 60 degrees. Now, this one is not on page 13, and we will have to use our formula, our calculators. We could have used our calculators for the other one, but if you've page 13 open, look, I did 3 of those as quick as I'd have the first one typed into the calculator. So remember, when we work with cos inverse, what we're trying to do is find the angle. So into your calculator, right, let's write the cos inverse of 0.8. Make sure your calculator is in degree mode before you do that. And we get 36.9 degrees, correct 1 decimal place. So now we have something that looks a little bit weird, and it is express cos of the sine inverse of x in terms of x. So let's break it down piece by piece. Sine inverse of x. So basically what they're telling us is there is an angle A such that the sine inverse of x gives us A. Bringing it backwards, we're basically told that the sine of this angle is A. Let's put A in a little right angle triangle here, and let's remember that sine is opposite over hypotenuse. Any whole number can be written over 1, so that tells us that the opposite is x and the hypotenuse is 1. So they basically have asked us to find the cos of sine inverse of x, which is basically cos of A. So the first thing I need to do is I need to work out my adjacent side. So there's my opposite, here's my hypotenuse, and I'm going to work out my adjacent. So we know using Pythagoras, the hypotenuse squared is equal to the opposite squared plus the adjacent squared. Or if you prefer, CAB, so C squared is equal to A squared plus B squared. Whatever way you want to work it, it'll work out the same. So 1 squared is equal to x squared plus this, which we are going to call the adjacent squared. So the adjacent is going to be the square root of 1 minus x squared. Not very pretty, but this is what we have for the adjacent. So that's this side here. So to work out cos, we're going to use the adjacent over hypotenuse. So my adjacent is the square root of 1 minus x squared all over the hypotenuse, which is 1. So the cos of A is the square root of 1 minus x squared. We did work with some questions like this, but much simpler in the Junior Cert revision. It's also at the start of the trigonometry video, which covers the ratios and formula. This is bringing it to the next level. It's bringing it up to higher level. It's working with our algebra, and it's something that could confuse a lot of students, but we really are just using sine and cos and Pythagoras. So example 21. Evaluate sine of 2 tan inverse 4 over 3. So first thing we want to do is talk about this as an angle. So effectively this thing here is A. So we're basically asked to find sine of 2A, where A is equal to the tan inverse of 4 over 3. So that means that the tan of the angle A is 4 over 3. Tan means opposite over adjacent. Here's my angle A, here's my opposite, here's my adjacent, here's my hypotenuse. So I know this is 3, I know this is 4, and my hypotenuse then works out as 5. You can work that with Pythagoras, or you might recognize this. This is one of our Pythagorean triples. It's probably the most common one. So when we have a right angle triangle and the two shorter sides are 3 and 4, the longer side will always be 5. Okay, but you can work it through if you've any issues getting that. So from this triangle, I'll be able to get sine or cos, but remember what we're looking for is sine of 2a. Now, sine of 2a we won't be able to pull because it's a double angle, but what we're going to do, we're going to go to our log tables and look at the double angle formulas, and they are on page 14. So for sine of 2a, so I'll take this from page 14. So we're on the double angle formula, so the bottom half of the page, and we're taking the second one down on the left, and that is 2 sine A cos A. So we're just going to work in that formula. So 2 sine, if you want to work here, we can work out sine of A, soca toa, or whatever way you remember it. So sine is opposite hypotenuse, cos is adjacent hypotenuse, so 3 over 5. So sine is 4 over 5 times cos, which is 3 over 5, and that gives us 2 by 4, 8 by 3, 24 over 25, which is the answer of sine of 2a without ever touching a calculator. You can, of course, use your calculator. It didn't say you couldn't, but we want to show how you can work this through, focusing on not finding the actual angle and working as accurately as we can without our calculator.